All right, today we're looking at graphs of polynomials, and we're going to kind of look at a lot of different functions. We're going to come up with some new terminology for different functions and look at some commonalities between all of them. So what I'm going to do for each of these, there are going to be 6 functions we're going to study here. I'm going to tell you what the function's called. We're going to talk about the degree of the function, and then we're going to look at a graph of one. And this is just an example graph. Not all of these functions look exactly like this one graph I'm drawing. So our first function we're going to study is called the constant function. An example of a constant function would be like y equals 3, just a number. There is a degree of 0 because there is no x term. So an example of what this would look like is something like this. This would be a constant function where there's no increasing or decreasing intervals there. It is just a straight horizontal line. All right, the next function is a linear function, which we studied earlier this year. This has a degree of 1 because there is an x term. An example of this could look something like this. So you'll see it's a slowly increasing function. I would say this is an interval of increasing here because our slope is going upwards. And it's a continuous and linear increase. All right. The next function we have is a quadratic. This is the one we just got done studying. This has a degree of 2 because the highest exponent is 2. That could be possible. An example of this could be, if you look here, we have 2 different intervals. Our first interval here is a decreasing interval right here. And then at this minimum point, it switches to an increasing interval. This point right here is a new vocab word. We would call this an absolute minimum. The reason we call this an absolute minimum is because it is the lowest point possible on the graph. There are no other points lower than it. If we have a negative quadratic there would be an absolute maximum. But that is an absolute, it's the lowest point, nothing will go lower. The next one is what we call a cubic function. This has a degree of 3, so it's x cubed. An example of that would look something like so. If you look here, we start off with an increasing interval. Then we get to this point right here, and then we have a decreasing interval. Then we get to this point, and then it goes back to an increasing interval. So if you notice, each time we gain a function, we gain another interval, whether it's increasing or decreasing. Now, these points are not going to be absolute minimums or maximums here. Reason being, there are points higher than them because our arrows are going different ways. So I would call this point right here a relative maximum. Reason being, it's on an interval, so you've got an increasing and then a decreasing afterwards. All right, so it is a high point, but it's not the absolute highest point. It's just a little hilltop there. This point right here, I would call a relative minimum. Again, it's on the interval from decreasing to increasing. All right, it's not the lowest point possible, but it is a very low point in the general area on that interval. All right, up next, we have a quartic. Function. This will have a degree of 4. A quartic function is going to look something of this sorts. All right, so we've got an increasing interval, And then we've got a decreasing interval. We've got another increasing interval. And we've got another decreasing interval. So we have 4 different intervals here. Now this point right here, I would call this an absolute maximum because it is the highest point possible, nothing is higher. Whereas this point right here, I would call a relative maximum. Because while yes, it is a high point on that interval, it is not higher than that first point. I would call this point right here a relative minimum. Okay, so you can have relatives and absolutes all in the same picture. And the final function we're going to study is a quintic function. This has a degree of 5. So a quintic could look something of this sort, where I think this point and this point here are both going to be relative minimums. And this point and this point are both going to be relative maximums. There are no absolutes because those arrows are going to go extending forever and ever. We've got a lot of intervals too. We've got a decreasing interval, then increasing, decreasing, increasing, and decreasing. So I want you to look at all these real quick for me. I'm going to ask you some questions about these. So my first question is, which functions have absolute minimums? So look at all these. Which ones actually had absolutes? So the ones that had absolute minimums or maximums are right here and right here. So the functions that have them are even degrees. Okay, so let's write that out. Let's take a note there. Even degrees have absolutes. Okay, they're going to have an absolute high point or absolute low point depending on the situation. Next thing I want you to kind of look at, what do you notice about the even functions? So what do you look over here with the quadratic and the quartic? What do you notice about them? Is there a trend? I'm hoping the trend you see is the arrows. If you notice, their arrows, their end behavior, they're both going the same direction. So for even degrees, their arrows are going to be the same. They're either going to be both up or both down. Whereas on the odds, if we look over here on our odds, the arrows for odds are facing different directions. All right, so that is a commonality. So now that we've seen this, we're going to kind of piece some more ideas here together about graphs of these polynomials. So go ahead and pause this and write down this little summary table. We're going to be looking at the end behavior. Remember, end behavior is as we approach the infinities, x as approaches negative infinity and x as approaches positive infinity, what are your y values doing? And that's all about the degree and the leading coefficient. So we said before here that right here we said even degrees are going to have the same arrows and odd degrees are going to have opposites. Okay, now the leading coefficient tells you what your last arrow is going to be doing. So for example, we know that even degrees, they're going to be the same. So they're either both going to go up or they're both going to go down. For the odd degrees, we know it's going to be one or the other. For the leading coefficient, your second arrow is going to be facing upward if it's positive. If the leading coefficient is negative, it's going to be facing downward for the second one. And positive means like if the first coefficient is a negative or positive, so it's like 2x squared would be a positive leading coefficient, whereas negative 3x squared would be a negative. So let's draw some example graphs here. All right, so if it's an even degree and a positive coefficient, we know our second arrow has to be facing up And since it's even, they both face up. So you can just make any kind of function that would both be facing upward. So the key thing here is that both arrows are facing upwards. If it's an odd degree and it has a positive leading coefficient, you know the second arrow is going to be facing upward, but your first arrow is going to be facing downwards. So I can make something like that. And again, we get that positive there from that positive leading coefficient. For negative, we know our second arrow is going to be facing down. And since it's an even degree, they both face down. So it could look something like this. Again, both those arrows are facing down. If it's negative leading coefficient in an odd degree, you means your second arrow is facing down, but your first one's facing upward. And again, that arrow is facing down. So the odd degree tells you that we're going different directions, even degree says the same direction, and the coefficient tells you what that second arrow is facing. So here's how we use this. We're going to actually start looking at end behavior without ever even graphing a polynomial, and we're going to know kind of what it looks like. So this first example says here, state the end behavior of the polynomial, and it gives us this polynomial. F of x equals negative 4x to the 7th minus 3x to the 6th plus 2x to the 5th minus 3x plus 5. That's a lot, so we can kind of break that down. So based on the degree, we can tell a lot from it. So our degree here, if I look at my degree, remember that's the highest exponent, my degree is 7. So that's an odd degree, which means my arrows are either going to be looking like this or this. They're going to be going different directions. Okay? So the degree tells you the directions of the function. Now, the coefficient here, the negative coefficient, tells me my second arrow has to be facing down, which means out of these options is going to look something like that. So here I can make a fake drawing of what I think this graph could look like. It's, again, this isn't a real drawing, but I'm thinking it's going to look something like this. So we can do the end behavior. So my end behavior would be as x approaches negative infinity, as x approaches positive infinity, remember, this is all about which way the arrow is facing. So as x approaches negative infinity, that is this arrow here. Which way is that arrow facing? It's pointing upwards, so that'd be to positive infinity. As x approaches positive infinity, that's this arrow down here, it's facing downwards, which is towards negative infinity. So this would be my end behavior without having to graph the actual function. All right, second example here. It says you have a 4th degree polynomial. How many real and complex solutions does it have? So we're going to draw an example of this real quick. So I'm going to tell you, here's my function. Okay, so here's my 4th degree polynomial. I want to know how many real and how many complex zeros it has. Now remember, another word for zero is roots, x-intercepts, solutions, etc. We'll talk about zeros, looking for those solutions there. So 4th degree. Your degree, okay, tells you the number of zeros your function will have. So since this is a 4th degree, we're going to have 4 zeros in total. Like we said before, we either have a real solution or the complex. Now on a graph, we can only see real solutions, and your real solutions come from your x-intercepts. In this graph, I've got an x-intercept right here and an x-intercept right here. So I've got 2 real solutions, and I get this from my x-intercepts. If I have 2 real solutions and the total amount has to be 4, that means I have to have 2 complex. Okay, and I get that by doing my degree, so 4, minus the number of reals I see, which would be 2. As a little side note here, your complex solutions always come in pairs or sets of 2. So you'll never just have one complex solution or 0. It'll be 2, 4, 6, etc. All right, so here's where we're headed with all of this. We are now going to sketch and analyze a polynomial. We've done this with linear functions, and we've done this with quadratics, but now we're gonna do it with actual polynomials. So go ahead and grab out your graphing calculators. We're gonna do this together. So we're gonna graph this. So I have already typed this into my graphing calculator. So x to the 4th minus 4x cubed plus 12x minus 3. And I'm push the graph button. And it gives you this polynomial. So what we're gonna do is we're gonna go and kind of sketch this real quick on our thing. So if I do this, it looks something like this, if you remember. Ooh, that's a bad one. Try that again. Yeah, it doesn't have to be perfect. This is just a sketch. Okay, but that's what it kind of looked like. All right, we need to find the big points here. So we need to find our maximums and a minimum. So what we're gonna do first is we're gonna try to find this minimum point here. We wanna be as precise as possible. So how we do that is you push the second button and then you push trace. And this, because so we've used this one before with like the zeros or the value, you're gonna scroll down till we see the word minimum and push enter. Now yours not be the exact same. You're gonna put some little flasher here. So here's mine, it's like a little X I'm kind of toggling around by pushing the arrows back and forth. The first question is it left bound? So you wanna see if that little X is left of your minimum, and it is, so you push enter. Then you move it so it's to the right of that minimum, push enter. And right here on my screen, it's that first line here, it says P1. That means my minimum is at negative 0.879, comma, negative 10.234. So I'm gonna write that in. So this point right here is at negative 0.879, comma, negative 10.234. And we're going to find this maximum next and then this minimum next. All right, so we're going to move this over here. So we're going to do second trace. We're going to do maximum now. It's to the left that point, so we push enter. You're going to move it so it's to the right of that point, push enter. And mine says it's going to be 1.347, comma, 6.680. So 1.347, comma, 6.680. Let's go find that last one. Second trace. This one's a minimum, so we're going to go over so we see minimum. It's to the left of it already. We're going to move it so it's to the right of it. And it says here it's 2.532, comma, 3.554. .352, comma, 3.554. All right, so there's my sketch and kind of how I do that. So again, you only need to focus on those kind of mins and maxes. Notice here too, it's an even degree, so our arrows are both facing up, or facing the same way, and it's facing upwards because it's a positive leading coefficient. So now with this, we're gonna actually analyze it and answer all of these questions. Go ahead and pause this and write down all these questions. All right, so the first question is our domain. That means our x value. So our domain here is going to be from negative infinity to positive infinity. Our range is our y value. So I'm looking at this. I have an absolute minimum. I have a lowest y value possible. My lowest y value possible is at negative 10.234. So I would say my range is from negative 10.234. My highest y value is those arrows facing upwards. So that'd be to infinity. All right, my absolute maximum. Do I have an absolute high point? No, because my arrows are pointing up. So I would say NA, there is no absolute maximum. Do I have an absolute minimum? Yeah, I have a lowest point possible. This is the very first point we found. So my absolute minimum would be negative 0.879, comma, negative 10.234. All right, relative maximum. I think this point right here is my relative maximum because it is a high point, but not the highest point possible. So my maximum could be 1.347, and you can have multiple of these. Making my next point here, this little minimum, a relative minimum, because again, it's on the lowest point possible. We have a lot of points lower than it. Okay. Now the increasing and decreasing intervals. remember, we use x values for these, so let's kind of label what we know. So I'm going to take a highlighter, and I'm going to highlight all of the decreasing intervals. So from here to here is decreasing, and from here to here is decreasing. I'm going to highlight the increasing, so from here to here is increasing, and then from here to here is increasing. So I have 2 intervals of increasing and 2 intervals of decreasing. Now when I'm looking at this, again, I have to use my x values. Okay, so important point here, important point is there. So my x values that are over here are negative infinity. My x value right here is negative 0.879. My x value here is 1.347. My x value here is 2.352. So from here to here, we said would be decreasing, so that's the yellow area. So my first decreasing one would be from negative infinity to negative 0.879. And then at that point there, we're switching and we're starting to increase. Oops. So I would say we're increasing between these 2 values here. So I say my increasing interval is going to be negative 0.879 to the x value there is 1.347. Then at that point, all right, we start to decrease again. So then from here to here is decreasing. So from 1.347 to 2.352 would be decreasing. And then finally, we begin to increase again. So from here to there is going to be increasing. Remember, this is going to be a positive infinity over here. So I'd say my increasing interval is going to be 2.352 to infinity. All right. Up next, we have the y-intercept, so where it crosses the y-axis. It crosses the y-axis. To find that, we're just going to take it and to find the y-intercept, you just plug in 0 for x. So if I plug in 0 for x up here, I get 0 to the 4th minus 4, 0 cubed plus 12 times 0, and I am getting negative 3. So the hint for that one is plug in x equals 0 to your function. And now we have our end behavior. So remember, we started off the same as x approaches negative infinity, as x approaches positive infinity, as y approaches, and as y approaches. All right, so if you look at our end behavior, as x approaches negative infinity, which way is our arrow facing? Well, our arrow is facing up for both of them, so they're both to infinity. Now the next part, the real roots and the complex roots. Now we know it's a degree of 4, okay? So we know these two have to add up to 4. The real roots are your x-intercepts, all right? So your x-intercepts are right here and right here. So we have 2 x-intercepts.